recording, and now I'm sharing my screen. So there is a reading that I have uploaded, Zhang et al. In the material folder, organization research method. So if you go to multi-level in the materials folder, multi-level, you have this paper. Okay, this is the paper I had mailed. And if you go to data in R scripts and in multi-level, I have uploaded this multilevel_med.r. Okay, so you can download this file as well. Okay.
Thank you, sir.
Yeah. Okay, so let me share my screen. We are going to look at another example today, and we will look at, in this example, we will look at both moderation as well as mediation. So So this is an example that is given in Blease. I had asked you to read it over the weekend. Okay, we will look at this data. And so first, let's look at the moderation data, something that we have been doing. So this is a military data. Okay, level 2 is platoon. Okay, and level 1 is cadet. Okay, and the outcome variable is well-being, and we say ij, well-being ij, and we say that hours that the cadet is working, so hrs ij. So hours is the number of hours a cadet is working, and well-being. So the idea is that the more number of hours you work, lesser is the well-being. And then we are also wanting to study that leadership has an impact on well-being. So if you have positive leadership, then you will have higher well-being. And we are also saying that group.hrs, which is nothing but the number of hours on an average the platoon is working, the platoon to which you belong or the company to which you belong, on an average the number of hours that platoon is working, the higher number of hours the platoon is putting in, lesser is the well-being. And this variable, second order variable group.hrs, also moderates this relationship between leadership and well-being. That means if there is a platoon which is working more, then leaders will make a higher, we can argue that if you are more overworked or you are overworked, then if you have a positive leader, your well-being increases faster, because then that leadership maybe makes more impact compared to a platoon where you are already not working so hard or maybe not putting in so much of time. Then the leadership to well-being relationship may not be that steep. Okay, so that is something that we are trying to look at.
Sir,
This is an example. Yes, yes,
sir, so the group.hrs, that is the average number of hours the whole
yes,
platoon is
yes.
working. Okay.
G.hrs is the, we will use this notation, you can say, is the group mean, group average of hours put in by group members. Is that okay, Nivedita?
Yes, sir. Thank you.
Hmm? Hours is simple. It is the hours worked. Well-being is simple. Okay, so we have three L1 variables: HRS, IJ, lead, IJ, and well-being, IJ. And there is one L2 variable which acts as a moderator. We say it is HRSJ, which is nothing but the group mean of hours worked, right? Right. So now I am writing the equations. I will write it only once now. Okay. Then we will do it on R and SPSS. So the first step we know is step 1 is our null model, right? So what is the null model? We say well-being ij is equal to beta 0j plus rij. There is no, what is a null model? A null model is a model where you have no explanatory variable, right? And then beta 0j is equal to, what is the notation? Gamma 00, right, Richa? So it means 00. Why the first 0? The first 0 is associated with beta 0, and the second 0 is because it is the first variable in this equation, right? Gamma 00 plus u0j. So we will get the equation as well-being ij is equal to gamma 00 plus u0j plus rij. This is the null model equation that we have always studied. Now what do we do? Using this equation, we will find our ICC1, which is equal to sigma square u0 divided by sigma square u0 plus sigma square r. We will also get ICC2 here, which will tell us whether well-being, the mean of well-being varies significantly across groups, which is nothing but we have studied MSB, mean sum of squares between minus sum of squares within whole divided by MSB. And we have studied that this should be greater than 0.70. Right? This is what null model is. Then we come to step number 2. Okay, which is, okay, let us stop here and then go to R first, and let's do our null model equation. Okay, null model. So let us do this. Let's go to, let me start R. Okay, and I have started R. And now what I will do is I will first set my working directory, which is on my desktop, and open. And then last time I was telling you, when you set your working directory, you also load your workspace. Now last time I saved, so you will get this as your workspace .r data, which will be in your working directory. So we open this, and you see, once you open, everything that you had done in the last session loads automatically, right? This is the advantage of doing this. And then we open our file multilevel.r. This is the file multilevel.r. That is the file that we are going to work today. Okay, you don't have to install packages. You will just link the package. So we will say library multilevel. right? And this data that we are going to work is already existing in this package, okay? Because let me also open Bleeze document, okay? And I asked you to read from page number 39, so let me go there. Mixed effects models for multi-level data, okay? So this is the reference. You should also go back and read it, okay? And we are going to look at, let me go to steps in multi-level modeling. Examine the ICC for the outcome, step 1, okay? Because multi-level modeling involves predicting variance at different levels, it is important. So he explains, and you see now he has written these two equations, Yij. Okay, so for people, Richa and others who were asking why should you use these notations gamma 0, 0, this is a very standard notation. Okay, this will not change in any multi-level textbook. You will always find this notation. Okay, so this is the null model. Yij is equal to gamma 0, 0 plus u0j plus rij. Okay, and that is what, and he has given these lines also, which I have written in the art script. Okay, so this is something that you should, for your reading also, you can read this, keep this document handy. Okay, please, document that I have given, and then the R script that we are working on is multilevel.r. So let us read the data. We'll say data BH 1966. And if you now you see it has red, and if you click on this data, you see group, cohes, g.cohes, w.cohes. So this is group mean of cohesion. This is within group mean centered. I will explain these variables. For us, what is important is group, lead, hours, g.hrs, and well-being, right? You can ignore all the others. Well-being is our outcome, level 1. G.hrs is level 2, g.hr. HRS is hours worked. Lead is level 1 leadership. Cohesion is not there in this example, and group identifier, right? So this is what we have in the data. Now, I have also written in the script, W being is well-being of individual, lead is leadership, hours worked, cohes is cohesion among workers. So what is our null model? Null dot model is LME, well-being, fixed effects. So what was the syntax? Well-being regressed on 1, and random is equal to tilde 1, and it varies per group. Data is equal to BH 1996, control and method. This is something that we will always use. Let us do this. Line number 17, line number 18, we have got this as the output. We have got the AIC, BIC, log likelihood, right? This is the random effects, standard deviation for the intercept and the residual. Then what is our, if I say where core, I have not written that, but if I say null dot model, okay, you see this is the variance 0.035 and 0.7895. So what is going to be ICC? It is 0.035. We can correct this. This is a small difference, 0.0353 divided by 0.0353 plus 0.7895. This is going to be our ICC1. Can anybody interpret this? 0427 ICC1. Who will interpret what this ICC1 means?
The 42%, how much? 44% only. 4.3% is explained by level 2 variables.
Level 2 variables.
Variance
Very good. Very good. 4.3% variance in well-being can be attributed to level 2
level 2.
or can be explained by level 2. Remaining close to 95% variance is at L1. Then I have written on line number 21, right? This is also something that we have learned using ANOVA command. Well-being as dot factor, the grouping variable group, data is equal to BH1996. You do ICC1, you get about the same 4.3, and you do ICC2, you get 0.77. So the mean of well-being significantly differs per group. That means groups differ significantly on their well-being scores. Then line number 26, I have shown you gmanrel. This is another command around the same. You get 4.3% as ICC1 and 0.73 as your ICC2. Then line number 31, I have said if we were to model well-being as one level regression only instead of multi-level, okay, so we do generalized least square, well-being regressed on 1, okay, so you get null.model.2, and if I do ANOVA command, okay, we get null.model. This is the AIC BIC, and so there was another question I think Richa had asked, why should AIC and BIC decrease? It is telling us that the deviance is smaller. That means your chi-square is approaching 0 or is, so a better model is one in multi-level which have lower AIC, lower BIC, lower deviance. Okay, this is how we test the fit of the model. So you will have to remember a good model is one which has lower AIC, lower BIC, and lower deviance, and deviance is minus 2 times log likelihood. So here it has reported log likelihood, you multiply it with minus 2, you will get that deviance. And we have also studied in our previous example that the difference of two deviance follows a chi-square distribution, so you can test it as a likelihood ratio. So we see that, okay, tell me which of the two models is good in this, which of the two models is better, null model or null.model.2, which model is better?
Model 1, sir.
Model 1,
1.
which means null dot model because it has lower AIC, lower BIC, and we can also see that this difference delta deviance is significant, right? The delta DF is only 1 and delta deviance is 187, which is highly significant, which is telling us that the two models are significantly different, and which is a better model which has lower AIC, BIC, and log likelihood. So our multi-level model is actually better, so we should go ahead and try doing multi-level modeling. Okay, so that is what we are. Now comes the random intercept model. Now before I go there, let us write the equation of random intercept model. Now what is the random intercept model? We are saying random intercept model. So we are saying our well-being ij is equal to beta 0 j. Now let us bring in uh, our uh, predictors. Okay, let us For the time being, what we will do is we will go ahead with, just let us bring our first predictor, which is HRS IJ plus RIJ. And then we say beta 0j is equal to gamma 00 plus, let's say we bring in group.hrs, g.hrs j plus u0 j, and we then say beta 1j because this is random intercept, so we say this is some constant gamma 10, right? And then we plug in, so what do we get? We get well-being ij is equal to gamma 00 gamma 01 g dot hrsj plus gamma 10 hrs ij plus u0j plus rij. What will be our R command? It will be LME, right? It will be well-being is regressed on 1 plus G dot HRS plus HRS, comma, random effect, random is equal to tilde 1 and it varies per group, and data is equal to BH 1996. Right? Simple. This is going to be our fixed and random effects command. Right? At the moment, we have just brought in HRS and G.HRS, the direct effects, into our model. So now let us go and do this in R. So you see, I have written line number 35. I have written model.1 is equal to LME, well-being regressed on HRS plus G dot HRS. I had told you in the last class also that we write 1 plus HRS or we don't write, it automatically takes the intercept, right? So writing 1 is not at all needed if you have other variables. But even if you write it explicitly, it doesn't matter. Then random is equal to tilde 1 and it varies per group. Data is equal to BH1996, and this is something that we have put already. Now we run this and we do the summary. Okay, you see AIC and BIC, they have reduced even further. Okay, then you have got these residuals, random effects, and these are the fixed effects, intercept, hours worked, and G dot HRS. They are all significant. So we say more number of hours worked, lesser is well-being. Okay, 1 unit change in hours worked, well-being decreases by 0.05. More number of hours worked as a platoon, well-being decreases by 0.13, and they are highly significant. So hours worked and group hours work, they both have negative relationship, which we were also expecting in our model, right? This is what we were hypothesizing, that hours worked will have negative relationship and group hours worked will also have negative relationship. What have we found? That this has minus 0.05 and it is significant at double star here means, let's say p less than 0.001. Okay, or even triple star we can write. So triple star less than 0.001. Similarly, this one is 0.13 triple star. This is what we have found in our analysis. This is what the results are telling us, that they both have, after modeling for multi-level effects, we can say that group hours worked and hours worked, they both have negative relationship with well-being. Right, this is what we have concluded. Now let us also look at if we can compare,
सब हमने वरुण से सीखा
the two models. So we can just write, I have not written it in the script, but now you know, you can compare it with null dot model. So we say model dot 1 comma null dot model. Okay, and you see which is better. This model has lower AIC, lower BIC, lower deviance and than the null model, and the difference is highly significant. So bringing in these terms have actually improved the model, as our AIC, BIC and deviance have gone down. Okay, now let us come to the third model, which is the random intercept and random slope model also, which is step number 3. So I will write it here. Step 3, random intercept and random slope. You see, we had already tested, we have got this path, this path. Now we want to find answers for both these paths as well. So these are the two paths, and because this is a moderating path, so it means this will be a random slope. This path is going to be a random slope model, right? So what is going to be our equation? We will say well-being ij is equal to beta 0j plus beta 1j hrs ij plus beta 2j. Now we will bring in the second L1 predictor, or let me write it in front itself in continuity. Let me zoom out a little bit. So we say beta 2 j lead ij plus rij. This is our L1 equation. Now you have two predictors. You have HRS and you have lead, right? There are two predictors, HRS and lead. Then we say beta 0j is equal to gamma 00 plus gamma 01 g dot HRS j plus u0 j, right? This has, we have modeled the direct path from g dot HRS to well-being. Then we say beta 1j, because that beta 1j is not being moderated, so we will hold it as the constant. This slope is not varying because our HRS ij to well-being relationship, that is not being moderated. What is the relationship that is being moderated? It is the relationship from leadership to well-being. So we say beta 2j is equal to gamma 20, right? Remember, we said that the first coefficient is always associated with the beta. So it is going to be gamma 20 plus gamma 21 G dot HRS. G dot HRS is the moderator plus we can say U1J. You can say U1J or U2J, doesn't matter. It only means that the intercept or the slope varies. So we can say u1 u2. It means that there is now one random intercept and one random slope. These are all our L2 equations. When we combine, what is it that we are going to get? We will get well-being is equal to well-being ij is equal to gamma 00 gamma 01 G dot HRS J plus gamma 10 HRS IJ plus gamma 20 lead IJ plus gamma 21 now product G dot HRS J multiplied with lead IJ plus U0J plus U2J multiplied with lead Ij plus Rij. How many fixed effects? 1, 2, 3, 4, 5. So you will have 5 fixed effects. How many random effects? 1, 2, 3. 3 random effects. And remember, you will have one covariance term of U0 and U2J. So the total number of parameters df is equal to 5 plus 3 plus 1. Yes, Deepak.
Sir, I have two small doubts.
Yes.
In random intercept model,
Huh.
we did not take the that lead
Yes.
variable.
Yes.
It is like our assumption intentionally, or it is
Actually,
not supposed to.
you can write it also. Doesn't matter. I could have written. You see, I could have also written this random intercept equation like this also. Doesn't matter at all. So don't don't get don't think that we have to write it only like I have written. Once you
Okay.
get a hang of this, you can also write it like this here also. You see, we could have
Yeah.
written beta 2j lead
Into
ij
lead J.
lead ij. This
Plus
is
Rij.
another formulation. You see, you can have just like regressions, we can have multiple
Yes.
formulation. Random intercept, I could have written like this also. Doesn't matter at all. You could have written gamma 00 plus gamma 01 G dot HRS J plus U0J, and then you could have written beta 1J is equal to gamma 10. You could have written beta 2J is equal to gamma 20.
20.
So you would have got your overall equation as well-being Ij
Okay.
is equal to gamma 00
An addition of both.
plus gamma 01 G dot HRSJ plus gamma 10 HRSIJ plus gamma 20 lead ij plus u0j and rij. So your command would have become LME. Your command would have become well-being regressed on 1 plus g dot
1
hrs
plus
plus hrs
HR SIJ
plus
plus lead ij
lead comma random is equal
and
to tilt 1 varies per group and data is equal to BH1996. So there is no assumption here, Deepak. It is just
okay.
that, and let me be honest, this is how he had demonstrated it in the example, in the PDF, right? That is what I have tried to reproduce. But otherwise, you could have straight away done this as well. You could have done it like this, okay, and
Yes,
then introduced the random slope also. That is perfectly fine. Understood?
thank you, sir. Yes,
Yeah.
thank you.
Any other question? Right, so let us go and do our random slope now. We have done random intercept. Now let us go and do our random slope in the file. Let's go to our R now and let us come to line number 40. You see line number 40, I have written model.2 is LME well-being and actually you see I have here, okay, I have done um, uh, there are two things that I have done. Okay, let me explain. I have done HRS lead and G dot HRS and random is equal to tilt lead and GRP. Can anybody guess what have I done here? I have modeled random slope, but I have not brought in the predictor of random slope. Okay, so if you see in model.2, what I have done is, let me just show. Can anybody decode this? I give you 2 minutes. Think about what is happening in this statement. You can raise your hand in the participant window. Anyone? If you look at line number 40, what is this syntax trying to do? Yes, Richa?
Sir, according to my understanding, well-being is affected by HRS, leadership, and group HRS.
Yes.
And in random effect, जो लीडरशिप पे जो इफेक्ट हो रहा है वो ग्रुप एचआरएस का हो रहा है, मतलब वो उसके अकॉर्डिंग वेरी कर रहा है, लेवल 2 का है वो।
ओके ओके, लेवल 2 का तो है. So what is this random effect telling us? And remember, it means this I have written 1 plus. If I have written only lead, that means there is random intercept and there is also random slope. One is automatically understood, so one I have not written, but it means there is a random slope associated with lead also. Okay, let me just explain what is happening here in model.2. In model.2, I have written this kind of an equation. I have written well-being ij is equal to beta 0j plus beta 1j hours plus beta 2j lead ij plus rij, and then I say beta 0j is equal to gamma 00 gamma 01 g dot hrsj plus u0j. Beta 1j I have held it at a constant, so doesn't matter. And now beta 2j I have written gamma 20 plus only u1j. I have not brought in g dot hrs. So if I combine these equations, what do I get? I get well-being ij is equal to gamma 00 gamma 01 g dot hrs j plus gamma 10 hrs ij plus gamma 20 lead ij plus u0j u1j lead ij plus rij. That means there is random slope, but I have not brought in no L2 predictor. There is no L2 predictor here. That would mean my command becomes LME well-being is regressed on 1 plus g dot hrs plus hrs plus lead. Simple. There is no L2 predictor, so there is no interaction term actually. And I have said random is equal to tilt 1 plus lead. Or you write simply lead, doesn't matter. You can, both of them are equivalent. They are equivalent. One is automatically, this is automatically understood. And then data is equal to 1996. Right, this is what is happening. I am saying there is random slope, but I have not brought in g dot hrs, right? That is what the command is. So you can see I have, let me also add it in the comment, no L2 predictor. And what was our L2 predictor? G dot hrs. So let us run this and we
Sir,
get,
here
yes.
actually no L2 predictor or not, we are not counting the interaction of L2 predictor only,
Yes,
because
yes,
if
there is random slope, but there is no L2 predictor for the random slope, right?
yes, otherwise for the random intercept we are
Ah,
considering it
random intercept. So no, let me write the full thing for random slope.
slope.
When I say no L2 predictor, it meant for the random slope, there is no L2 predictor,
Correct.
right? There is
Yes.
definitely a L2 predictor, but that was only for random intercept.
Intercept.
Right? So
Yes.
yeah, this is correct. This is the full comment. No L2 predictor for random slope. Okay, so we have got this. You see, there is now one more additional correlation that is coming up, which is between the U0J and the U1J or U2J. We can say the residual associated with lead. This is their correlation. Now the next line number 43, I say to determine whether the slope between leadership and well-being significantly varies across group. Okay, we test log likelihood. So I say if I, instead of modeling randomness of both leadership and intercept, if I have only intercept. Now Deepak, this is the model that you were asking. Now you see I have said update model to with a new random declaration, which is 1 and group. That means now do not keep leadership the slope as random, just have random intercept. That is why I have written update this model. So the Fixed effects will remain the same, but update them with this random effect, which means now keep only the intercept as random, do not keep the slope as random. Okay, so I say update model.to with the new random declaration and save it as model2. Okay, so I run this model and I do model 2 with 2a, and now you see it says there is a significant difference between the two models, and model 2 has a lower AIC, lower BIC, lower deviance. The difference in the deviance is significant, and therefore having a random intercept and random slope is better. Having a random intercept and random slope is better than having only a random intercept. Is this okay, everybody? Model number, model 2a. And now we come to the last model, which is where we are testing the cross-level effects. Okay, this is the model that we wrote. Now we are saying ours lead g.hrs, and now you see there is an interaction term, lead colon g.hrs. And you have, so if I were to write it correct, so let me add explicitly, there is an intercept, there is hours, there is lead, there is g.hrs, there is lead into g.hrs, and random is equal to tilt 1 plus. So both intercept as well as the slope associated with lead, they are going to vary. So the interaction, if this interaction comes out to be significant, I will consider that there is a moderation between leadership and G dot HRS. There is an interaction of the two. Let us run this command model.3 and we do summary. Now let us look at what has happened. This is our AIC, BIC, okay, and deviance. This is the standard deviation of intercept, of leadership, residual, and now you see hours, it is significant. So the more hours worked, lesser is the well-being. Leadership, the coefficient is positive, but it is not significant. You see, it is not significant. G.HRS, you see, it is significant and negative. So the more hours the platoon works, lesser is the well-being. And now you see you have an interaction between leadership and G.HRS. And is it significant? If you look at the p-value, it is significant at p less than 0.1. At 10% level of significance, it is significant. So we can say there is moderate evidence, okay, a weak evidence that there is an interaction between the between leadership and G.HRS. That means G.HRS is moderating the relationship between leadership and well-being. If I have to write it in this, in my diagram, how will I represent this data? I will say I had G.HRS, HRSJ, okay, then I had well-being IJ, then I had HRS IJ, then I had lead IJ, and then I had lead IJ multiplied with G dot HRSJ. These are all my terms, right? This is what I have got. So HRS IJ, we see the HRS, it is minus 0.03. It is significant at 3 star. G dot HRS, it is minus 0.175. It is significant at 2 star. Lead, it is 0.125, but it is not significant. And this interaction term, lead into G dot HRS, it is 0.032. It is significant at 1 star. 3 star, we can say, is P less than 0.001. 2 star, we can say, is significant at P 0.01, and 1 star is P less than 0.1. This is the result that we have got. This is what, and we can say this was L2, this was L1. Now let us do the plotting also. If we were to plot this, so I have written, now you see I have written variance of slope accounted. Okay, so we can compute how much is the variance of slope. So without having random, you can see without bringing in G dot HRS, this interaction, the variance of slope was, of leadership was 0.0102, and in the third model it is 0.009. So this is what I have written. How much variance is accounted by bringing in G dot HRS? It is nothing but the difference 0.0102 minus 0.0091 whole divided by. So this is the variance accounted. You can say 10% randomness in the slope has been accounted by G dot HRS. So you can say this, that 10.87% variance in the randomness of the slope associated with lead has now been accounted for by bringing in this interaction term, or by G dot HRS. So if we have to plot this, now in our model we have 4 variables: HRS, lead, G dot HRS, right? So we have to set their values, and we have to plot it for 2 values of G dot HRS. So how will the plot be? What am I trying to do here on line number 58, where I have written plotting? I want to now show this on a graph also. Okay, how does it look? So what am I trying to do? I want to show that as leadership varies, okay, well-being varies. So well-being is the outcome, lead is the X, and I want to show it for 2 levels of, this is G dot H, because G dot HRS is the moderator. So I want to show a graph like this. If it is high, the relationship is steeper. If it is, so we can say dotted line and a solid line, right? One is for low, one is for. So what do I need? I need 2 values of G dot HRS, which is equal to mean plus minus 1 ST. In order to plot any 2 lines, we need two values. Okay, so we need to have two values of lead, which is equal to mean of lead plus minus 1 standard deviation of lead. Similarly, let me rewrite this correctly. So we can say G dot HRS mean plus minus 1 standard deviation of G dot HRS. And the last variable HRS, which is actually in the model, but we are not using it, we will put it at its mean value. So we will put it at its other variables in the equation, because we are interested in well-being, lead and G dot HRS. So the third predictor here in the equation, HRS, this we are going to say fix. You can fix it at 0, you can fix it at mean, doesn't matter. You can also fix it at, that is also possible. Okay, and we will do this graph. So this is what I have done. You see, I have written here line number 57, plotting the interaction. So I first compute the mean of G dot HRS and the standard deviation of G dot HRS. So you see, it comes out to be 11.30 and standard deviation is 0.86. So what is the low value of G dot HRS? It is mean minus 1 SD, and high value is mean plus 1 SD. So when I run this, I get two values, 10.44, 12.16. Then I do the same thing. What is the mean of lead and what is the standard deviation of lead? So I get 2.89 and 0.77. So mean minus 1 SD and mean plus 1 SD. These are the two values of leadership, 2.12 and 3.66. So I create a data frame underscore 99 because I want to do it for one platoon. So I say HRS mean is going to be the same as the mean of G dot HRS. So I'm going to hold it at a constant 11.30. Then lead, I keep it at low value 2.12, 2.12, 3.66, 3.66. And then G dot HRS, I toggle it 10.44, low value, high value 12.16. And then 10.44 and 12.66. And I say group is equal to, you can give any number, 99, okay, and I call it as data frame 99. So I do this, I predict, and then I create this data frame tdat, and then I use this wonderful command predict. I give it model.3. So use all the coefficients in model 3, use this data, okay, and do it for specific group 99 and predict the values and store it in this new variable well-being. So I run this command. Similarly, I can do it for overall data, okay, and here I just say level is equal to 0. Everything else remains the same. I create a data frame tdat. I predict the values of well-being. Typically, I would say even if you just do this line number 71 to 73, this is sufficient. You don't have to predict it for specific platoons. That is not at all needed. So I just create this tdat and then predict well-being, and then I will use that command, which is plotting, which is t_dat underscore 99 interaction dot plot, the x variable, the moderator variable, and the output variable. So let us plot this. You see our lines have come, and we are seeing that for higher g.hrs the slope seems to be slightly steeper than for lower g.hrs. That is for, and remember our interaction term was slightly significant, only at 10%. That is why you don't see a very major change in the slopes of the two lines, right? That is understandable. Leaders impact well-being. The impact of leadership on well-being is steeper for groups that have higher hours worked. That means groups that are more worked. In those groups, leadership seems to have a positive relationship, a slightly more positive relationship with well-being as compared to groups, but the slopes change only slightly. Okay, and let us do it for the overall. This is actually the data that we typically use. This is what you will have to report with the overall. Yeah, here you see the results are slightly more visible. We see that for 12, okay, g.hrs 12, you see the line is slightly, we can say, steeper. This slope for 7, this slope seems to be slightly less steep than for the group which has on an average 12 hours of work reported. And that is what we are seeing, that the level 2 variable has significantly moderated the relationship between leadership and well-being. So this is how we will test moderation. This is how we will report moderation. This is how we will draw these graphs and put them in our papers, right? Let me take a pause and see if there are any questions. Is this okay with everybody? All right, so let me now show it how we will do it in SPSS. Okay, how we will do the whole of this in SPSS. So I have given you a data file. If you look at the data in our scripts, multi-level, I have given you a data frame bh1996.sav. This is the data. Okay, if you open it, you see this is, I had cleaned that file. Okay, so we have only these three variables: lead, HRS, and well-being. Right now we know GRP is our grouping variable, lead is the leadership reported, hours is the hour worked, and well-being is the. Now the first thing is we will have to create g.hrs. Okay, in the R data we had g.hrs, right? But in SPSS we don't have it. So how we will do it? We will do, remember we had said in our earlier class, we had said we will use go to data and we will use the aggregate command. Okay, so we will go to data and then aggregate, right? Now what is the breaking variable? Grouping variable. Breaking variable means grouping variable. And what is the variable for which we want to take the mean? It is HRS. So you bring in as summaries, and the default is HRS, the mean of HRS. So I will change it. I will just change the name. Rather than saying HRS underscore mean, I am going to give the name g.hrs. Continue. So now you see it has changed the name. G.hrs is equal to mean, right? So you can change it from, and add aggregated variable to active data set. Yes, and I will paste it in a syntax. So I am going to write it Platoon data, okay, and I will say creating g dot hrs variable, okay, and I will run this command. Okay, and the moment what happened, it is okay, so it has saved and we have a g dot hrs that has been created. You see it has taken the mean for one group. This was group 1, so the mean of all the cadets, okay, 73 cadets in platoon 1 is 10.97. Then this is the second mean for the second platoon, then for the third platoon the mean is 10.44 and so on. Okay, so very easily it has done. Now we will do the first model, which is the null model. So we will go to mixed models and linear mixed models. The subject variable is group. This is the grouping variable. Okay, continue. Null model has no explanatory variables. Okay, no explanatory variables, so we will leave it as it is. Only dependent variable, which is well-being. Fixed, nothing, we will just say include intercept. Continue. Random, we will say include intercept, and we will say the combinations are based on group. Continue. Estimation, we will keep it at maximum likelihood, everything else remain the same. Continue. Statistics, we will say parameter estimates, we will say covariances of random effects, covariances of residuals. Continue. Everything else we don't have to change anything. Save, nothing to be saved. Bootstrap, nothing is to be done, and we paste the command in our syntax file, and we will say running the null model. Okay, when we run this, you can see the parameter, one fixed effect of the intercept, one random effect associated with the intercept, and one random effect associated with the residual. So there are overall 3 parameters. You get your deviance, you get your AIC, you get your BIC, okay, all of this. You get your parameter, you get your fixed effect for the intercept 2.77, and you get your residual and intercept. So we can compute our ICC1, which is equal to 0.0353 divided by 0.0353 plus 0.789. I'm not going to do it because we have done it already. Okay, but the output is here. This is the output that you have to use. Now let us do our second model, which is random intercept, and we will now include all, okay, we will include our HRS, our G.HRS, and our lead. Let us include all the 3. So I am going to bring in all the 3 variables. Okay, this is the model that I am running, is what Deepak had asked me. So let me take you back to the whiteboard. The model that we are running now is going to be, I think this was the whiteboard. Yeah. So the model in SPSS that I am going to run now is this model, where I am bringing in the random intercept, and I'm going to bring in g.hrs. I'm going to have HRS as the L1 predictor. I'm going to have lead as the L1 predictor. So essentially I'm going to have intercept, g.hrs, HRS and lead. And random, I will keep only intercept as random. So this is the, you can say, step 2 that I am demonstrating in SPSS. For your own records, if you watch this later, you can keep this in mind. So this is what I am doing. I am bringing in HRS, the L1 predictor. I am bringing in lead, the L1 predictor, and I am bringing in G.HRS, the L2 predictor. When I go to fixed effects, I say HRS, main effect, add, lead, main effect, add, and G.HRS, the main effect, add. So I have got them all the three main effects now. Continue. Random, I say only include intercept because it is only a random intercept model at this moment. So I am saying continue. Rest everything is the same. I paste it in my syntax file and I say running the random intercept model HRS plus lead plus G dot HRS. Okay, I run this. So you see the parameters, you have the 4 fixed effects now: intercept, HRS, lead and G dot HRS. Then you have one intercept, random effect, one residual. So overall you have 6 parameters. These are your model fit indices, and these are the fit of, these are the estimates. Okay, HRS we see is significant at p less than 0.001. Lead is significant at p less than 0.001, and G dot HRS is significant at p less than 0.001. These are your sigma square R and sigma square U0 at this time. And the last model now is we are going to do our random slope model. Okay, so everything else here remains the same. In random slope, what we are going to do is we are going to add the interaction term as well of G.HRS and lead, and I say continue. And random, I will also add the random effect of lead. So there is one intercept and one lead, and you see the covariance type by default it is kept at diagonal, and we have said that the most accurate is unstructured. If we see that the SPSS will not be able to run with unstructured, we will go back to diagonal matrix, otherwise we will keep it as unstructured. So let's say continue. Okay, everything else remains the same, and I now paste the syntax and I say this is random slope and random intercept model, okay, which is HRS plus lead plus G dot HRS plus lead multiplied with HRS. Okay, and we can also say covariance random effect covariance structure is unstructured. Let us run this now. So it has actually run without giving us any problem. So we can actually hold this because this is the most appropriate. And you can now see the parameters are 9, 6, 5 fixed effects and 4 random effects. I had calculated that on the whiteboard. So we are getting 9 parameters, okay, and we are getting the estimates. Intercept is significant, hours worked is significant, lead has now become non-significant, HRS, G.HRS is significant, and you see the interaction term is significant but only at 10%, p less than 0.10. So we can say, which we were also getting, that it is significant at p less than 0.1. There is a slight interaction effect between leadership and G.HRS, and we can see the plot is something like this, which we have already drawn and seen. This is the kind of the interaction plot that we have. Okay, so this is the run, all that we have to do. So I will save this and I will also upload this in the day 4 recordings so you can refer to. So I will call it as syntax MLM, and what do I say, well-being.
Where I have some doubts for SPSS. Basically, sir, sometimes we are using variance component and sometimes we are using unstructured. Specifically, when we are going to random slope, we are using unstructured.
Yes.
So is it okay if it is interchangeable if SPSS is not running
Yes,
in
it
the
is.
random cases?
Yes. Were you there in the last class?
Oh, yes.
Yes. So remember what I had said, that the most accurate
Unstructured is the best.
is the best. But there, if you remember, we were getting an error, right? We
Yes,
were
yes,
getting a
yes.
warning that it cannot
Warning.
estimate. So if you are getting a warning, if we that is what I said, that we will first try with unstructured, but if we get a warning that it cannot converge, then we will go to the
Variance.
diagonal structure, right? Which is where you don't have the covariance. What is a unstructured and diagonal? Okay, let me just write it on the board once again for the benefit of everyone. What had we said? That okay, so the board has hung, but we had said that the unstructured random effects covariance matrix models or compute sigma square u0 sigma square. So what is unstructured? Unstructured will compute sigma square u0 sigma square u1, and it will also compute u0 and u1, correct? U0
Yes, sir.
and U1. So this is most appropriate or most accurate. I'm repeating it. So we will first try unstructured. But if we get a warning or error, whatever, if there is a warning, then what do? You go for the diagonal, which is default, which assumes there is no covariance, and it computes or it models a covariance structure like this. Is this okay? This is the first thing that you should try, otherwise go to this. Is this okay, Deepak?
Yes, sir. It's clear. And sir, second doubt is in the slope, I guess we are always taking like that only. The randomness is associated with the level 1 only while we considering slope, because here we put
So
it the
see,
lead only.
the randomness has come because you have specified that the slope associated with lead is going to be random,
Okay.
right?
Yes, yes.
The slope
Got it.
associated with lead is random now. If I had brought in HRS, then what am I saying? That the slope associated with both HRS and lead are random now.
And for random, we are taking factorial.
And then in the fixed effect, in order, what is causing the randomness? It is this term g dot
Interaction.
hrs,
G dot
and
HR
that
is
is why we bring in this interaction term g dot hrs and lead.
Sir, here we have put interaction, our main effect, and in randomness we are putting
We have, yeah,
which
and
either main effect or random.
in randomness, you simply specified that lead is also random now. One
So
was
that
present.
factorial is there always. That thing
Yeah, that doesn't
button.
matter. That doesn't.
Okay, okay,
This
okay,
has no. This has no.
okay. In
Import.
random, there is no point of it.
There is no point.
Okay,
In fixed, this is only needed when you are creating this term,
okay.
right? When, see, if I had written factorial, then also it will create the product. Terms must be
Mhm.
unique. So if I do this remove and I say g dot hrs factorial, then it adds lead g dot hrs and it includes g dot hrs into lead. So this drop down here in SPSS is only used to create
Create.
terms. You see, if I select all of these and I say all three-way, then see what happens. It will create this three-way term also.
Okay.
So this is only done in used to create terms. So I will remove it now. Main means only main. Interaction means multiply the two terms that you have selected. Factorial again, multiply the two terms you have selected, and so on. Is
Okay.
that
Understood.
okay? Yeah.
Yes, sir. Yes, sir.
So,
Thank you.
so this is only this drop down is only used to create. It has no significance once your variable is in this box. You can keep it anything, but this variable is the important variable that will be used in the analysis. Is it okay?
Yes, sir.
Okay. Good. So we have done this example. You can go back and try this again. This is all the example. This is all that he has said. Step 2, explain level 1 and level 2. You see all these equations he has given. Then this is the equation of random intercept model. Okay, and you may go back and read these. Okay, I have explained. Then predicting randomness in slope, you see this is the equation that we had written. This is what we have got. Okay, and
Sir, I have one more doubt.
yeah,
Sorry. Actually, the doubt is in SPSS we are getting all the values and ICC one.
you are getting
We are getting all the required values, intercept and their p value, and plus ICC one
in SPSS.
SPSS.
Huh,
So through the SPSS we are getting ICC one.
huh.
So sometimes some people using that parameter estimate, and then by some formula they are I guess calculating ICC 2 out of it. But is it okay if we get ICC 1 and that p value? That means we compulsorily need R
We need
plus SPSS
you can simply do it in SPSS, but computing ICC2 and
with some tau or something they are calculating.
ICC1 we have computed, right? Using
Okay.
But ICC2 and RWG, you can actually use R,
R.
those two commands. You just do ANOVA and
So better is use both the software.
you can use both.
Yes, yes, yes.
You should learn both. Or
Yes, yes, yes.
but in SPSS, I have not found a good way to compute ICC2 and RWG. That is the
So
main.
that means SPSS is not enough like that.
Is not enough. Yeah.
Yeah, okay,
It's
okay.
not enough.
Thank you, sir. Thank you.
Yeah. Okay. So read this document. What I was telling here is, you see this plot also has been drawn for 12 and 7. This is the kind of the plot that we got in our work. 7 and 12, you can use this. Okay, so read this example, and so let us take a pause here. It is about 4:40. Let us come back, take a 15-minute break, and come back at 4:55, and then we'll discuss few more things and then get into multi-level mediation.